Hello, this is the section Simple Linear Regression. In this section we'll introduce our first model, Simple Linear Regression. Simple Linear Regression models the relationship between one response variable and one feature of an explanatory variable. We'll discuss how to fit our model, and we'll work through a toy problem. While Simple Linear Regression is rarely applicable to real-world problems, understanding it is essential to understanding many other models. Now we move on to the first video of this section that deals with what simple linear regression is. In this video we'll examine simple linear regression, which can be used to model a linear relationship between one response variable and one feature representing an explanatory variable. We'll estimate the price of pizza as an example. Suppose you wish to know the price of a pizza. You might simply look at a menu. This, however, is a machine learning course, so instead we'll use simple linear regression to predict the price of a pizza based on an attribute of the pizza that we can observe, or an explanatory variable. Let's model the relationship between the size of the pizza and its price. First, we'll write a program with Scikit-learn that can predict the price of a pizza given its size. Then we'll discuss how simple linear regression works and how it can be generalized to work with other types of problems. Let's assume that you've recorded the diameters and prices of pizzas you have previously eaten in your pizza journal. These observations comprise our training data as shown here. We can visualize our training data by plotting it on a graph using matplotlib. This code is used for that. In this script, x represents a matrix of pizza diameters, and y represents a vector of pizza prices. The reason for this decision will become clear in the next section. Let's run this. The script produces this plot. The diameters of the pizzas are plotted on the x-axis, and the prices are plotted on the y-axis. We can see from the plot of the training data that there is a positive relationship between the diameter of a pizza and its price, which should be corroborated by our own pizza eating experience. As the diameter of a pizza increases, its price generally increases. Next, we're going to look at the pizza price predictor program. Here's the code. This program models the relationship using simple linear regression. Let's review the program and discuss how simple linear regression works. Let's run this. We get the output that a 12-inch pizza should cost $13.68. The linear regression class is an estimator. Estimators predict a value based on observed data. In Scikit-learn, all estimators implement the fit methods and predict. The fit method is used to learn the parameters of a model, and the predict method is used to predict the value of a response variable for an explanatory variable using the learned parameters. The fit method of linear regression learns the parameters of this model for simple linear regression. In this formula, y is the predicted value of the response variable. In this example, it's the predicted price of the pizza. X is the explanatory variable. The intercept term alpha and the coefficient beta are parameters of the model that are learned by the learning algorithm. Let's plot the hyperplane now using this script. The hyperplane plotted in the figure models the relationship between the size of a pizza and its price. Using this model, we would expect the price of an 8-inch pizza to be about $7.33, and the price of a 20-inch pizza to be $18.75. Now we'll evaluate the fitness of the model with a cost function. We'll plot a graph showing regression lines produced by several sets of parameter values. Enter the script for that. Here's the graph. These are the regression lines. How can we assess which parameters produce the best fitting regression line? A cost function, also called a loss function, is used to define and measure the error of a model. The differences between the prices predicted by the model and the observed prices of the pizzas in the training set are called residuals or training errors. Later, we'll evaluate the model on a separate set of test data. The differences between the predicted and observed values in the test data are called prediction errors or test errors. The residuals for our model are indicated by vertical lines between the points for the training instances and the regression hyperplane in this plot. We can produce the best pizza price predictor by minimizing the sum of the residuals. That is, our model fits if the values it predicts for the response variables are close to the observed values for all of the training examples. This measure of the model's fitness is called the residual sum of squares, RSS cost function. Formally, this function assesses the fitness of a model by summing the squared residuals for all of our training examples. The RSS is calculated with the formula shown here, where yi is the observed value and f of xi is the predicted value. Let's compute the RSS for our model by adding these two lines to the previous script. Our RSS is 1.75. Now that we have a cost function, we can find the values of the model's parameters that minimize it. Next, we'll solve OLS for simple linear regression. Recall that simple linear regression is given by the equation y is equal to alpha plus beta x, and that our goal is to solve for the value of beta and alpha to minimize the cost function. We'll solve for beta first. To do so, we'll calculate the variance of x and covariance of x and y. Variance is a measure of how far a set of values are spread out. If all the numbers in the set are equal, the variance of the set is 0. A small variance indicates that the numbers are near the mean of that set, while a set containing numbers that are far from the mean and from each other will have a large variance. Variance can be calculated using the displayed equation. X bar is the mean of x. Xi is the value of x for the ith training instance, and n is the number of training instances. Let's calculate variance of the pizza diameters in our training set. Enter this script for that. NumPy also provides the method var for calculating variance. The keyword parameter DDOF can be used to set Bessel's correction to calculate the sample variance. Here is our variance. Covariance is a measure of how much two variables change together. If the variables increase together, their covariance is positive. If one variable tends to increase while the other decreases, their covariance is negative. If there's no linear relationship between the two variables, their covariance will be equal to 0. They are linearly uncorrelated, but not necessarily independent. Covariance can be calculated using this formula. As with variance, xi is the diameter of the ith training instance, x bar is the mean of the diameters, y bar is the mean of the prices, and yi is the price of the ith training instance, and n is the number of training instances. Let's calculate covariance of the diameters and prices of the pizzas in the training set. Enter this script. You can see the output here. Now that we've calculated the variance of our explanatory variable and the covariance of the response and explanatory variables, we can solve for beta using this formula. Having solved for beta, we can solve for alpha using this formula. Here, y bar is the mean of y and x bar is the mean of x. X bar, y bar are the coordinates of the centroid, a point that the model must pass through. Now that we've solved for the values of the model's parameters that minimize the cost function, we can plug in the diameters of the pizzas and predict their prices. Congratulations! You used simple linear regression to predict the price of pizza.